Unless I mention it. Alright. Here's the child. 0 meters per second. Climbs up the ladder. 0 meters per second. Slides down the ladder. Comes to some velocity. We don't know what. There's no friction here. Mu is 0. Then there's friction here. The child comes to a stop. So not moving here, not moving there, not moving there. This is the length of the ladder. This is the height. This is the length of the slide. Alright, let's go. The child's PE and KE when he is sitting at the top. So he's 15 kilograms and PE is mgh, KE is 1/2 mv squared. So for PE I can plug in 15 kilograms times G 9.8 times the height 3 meters, and that gives me 441 joules. Kinetic energy is 0 because it's 1/2 mv squared, and at the top the child has no velocity. Part B. As the child climbs the ladder, what average force does the ladder exert on the child parallel to the ladder? So here's a simple way to do this. It just occurred to me. Since the ratio of the ladder's length to the height is 4:3, I can draw this diagram. Here's the height of the ladder. This is actually the, oh, what am I doing? Let me just do it. Let's see. So this is the child's weight. Then, oh yeah, well, I have to do a little bit more geometry here, but basically this is the vertical force. This is the force parallel to the ladder, and this would be the force perpendicular. And you can show that if the ratio of this to that is 4:3, then the ratio of this to this is 4:3, or more specifically that the parallel force equals this equals that times 3/4. And this is mg. So if you plug in the mass of the child, 15 times 9.8, 15 times 9.8 times 0.75, you will get the answer here. That is about 110. But here's another way of doing it. Using the law of conservation of energy for including non-conservative forces. So in this case we've got the kinetic and potential energy of the child at the bottom, and the kinetic and potential energy of the child at the top, and then this work done by the outside force. So this would be the force of the ladder. We'll consider the ladder to be outside the child in this case. So the potential energy of the child at the bottom is 0. The kinetic energy is 0. And that's because at the bottom there's no height for potential energy, there's no velocity for kinetic energy. So those are both 0. And then at the top, the child has potential energy because of the height. We've already calculated that, 441, but no kinetic energy. So in the beginning, the child has 0 energy, and then the child has 441. So that 441 must be coming from work being done by something outside the system. So we're considering that to be the work done by the ladder pushing the child. That's what's acting on the child in this case. So the work then, work is force times distance. F is the force of the ladder, D is the distance. The work is 441. Here I've plugged in the length of the ladder, and then I can solve if F times 4 equals 441, the force of the ladder is 110 newtons. Part C, how much kinetic energy does the child have at the bottom of the slide just before he or she slides onto the level surface? So now I can use this because there's no friction or anything between here and here. Nothing outside the child doing any work. So, except gravity, which is considered part of the child system, child Earth system here. So the potential energy at the top is this, kinetic energy at the top is that, child's not moving. Potential energy at the bottom is going to be 0 because there will be no height, and then kinetic energy at the bottom. So this kinetic energy at the bottom equals potential energy at the top, 441. We're just trading all this potential energy for kinetic energy there. What's the force of friction on the level surface at the bottom of the slide? So basically, friction is going to do work on the child until the child slows back down to 0. Friction is going to do work to take all this energy away. So whatever work friction is doing, it has to equal the energy that the child starts with here, and it has to be the opposite of that. But here's the, well, here's another way to do it. You could do this with probably with this formula. That would be fine. I've decided to use the work energy theorem, where the work done on the child equals the change in the child's kinetic energy, and the kinetic energy at the end point. This is just sort of the definition of the change in kinetic energy. So it's final minus initial. The final kinetic energy is 0. The initial kinetic energy is negative 441. No, the initial kinetic energy is 441. So the change in kinetic energy is negative 441. So just like I was saying, that it's got to lose all this kinetic energy to get down from here to 0. So the work done by friction is force of friction times distance. That's the distance that the friction does its work over. And here's the work that it does. So when you solve for friction, you get negative 29.4. And now E. This is the number of food calories in one Pez candy. And the child's digestive system, whatever, is 25% efficient at converting Pez candy into mechanical energy. How many climbs up the slide equal the usable energy in one Pez? So we need to figure out how much energy it takes to climb up the slide once, and then at 25% efficiency, how many Pez's that's going to take. So here's what I did. I said the work done by the child climbing the ladder is equal to the work done by the ladder on the child, and we already did that in part B up here. This was the ladder for, like, the work done by the ladder applying a force of 110 newtons over a distance of 4 meters. So basically the child is applying the same force, 110 newtons, over a distance of 4 meters. So doing 441 joules of work to climb that ladder. There are other ways to do this. I think you could probably use this formula again. So that's how much energy it takes to climb the ladder once. This, I'm just figuring out how many usable calories there are in that Pez. So 2.91 calories is 2,910 actual calories, and 25% of that's 727.5. So calories per Pez. And there are 4.184 joules per calorie. I've got to get to joules here, so I'm figuring out how many joules there are per Pez. So if I multiply calories per Pez times joules per calorie, calories cancel out, and I get 3,044 joules per Pez. And this is how many joules it takes to climb once. This is how many I have, so this is going to be way more than enough to do that at least once. 3,044 joules per Pez times one climb per 441 joules. joules cancel out, and I get 6.9 climbs per pez.